Righty then. Testing. Everybody hear me? All right. We live? We're going live. All right. Welcome, everyone. Welcome to this meeting of the Warren Astronomical Society. I am Bob Tremblay, your president. I'm a little that this meeting is taking place on the 11th, but oh well. So do we have any first timers here? We do have a first timer. Where'd you hear about us? Okay, cool. Hope you enjoy the meeting. Thanks for attending. All right. We haven't done this in a while. We used to do roll call. We're going to be doing that again, going around robin on the people here and saying who you are. And I'm all right, good. He's the LTV publication. Oh, he's the yeah. All right, so we'll start down there with you. I'm a 80%. Okay. Hi, Andrew. You're doing roll call, right? I'm the first vice president. Jim Shedlowsky, I'm an astronomer. Okay, continue on around that way.
My name is Eduardo Saluso. I became a member of March of this year.
Oh, hi.
Also astronomer. Good work. Our fifth year secretary. I want to be the
You look at the stars?
Yeah. You are.
Okay, continuing on.
Oh. Allison Baranski, excuse me. Love, second evening. Karen Hadley, presenting. So junior done.
Oh, hi there. Thank you. All right, so roll call is something we haven't done in a while, and thanks, Jeff, for reminding me we needed to do that. So, yeah, okay. Astronomy at the Beach is coming up, and near the end of this month, 22nd and 23rd, Friday and Saturday. If you plan on bringing a telescope or sitting at the watch table, and we do need you to do that, let me know at the break. The Metro Parks event organizers would like to say that they absolutely love Marty Kuntz. He did a fantastic job at the Kensington event. They were just gushing all about him at our meeting recently. So was Marty here? He's not. I wanted to give him a round of applause, but let's do that anyway. Thanks, Marty. They really love it. Okay, we have two more big events at Metro Parks. These are the last two of the year. These are both Night of the Dragon events. One's October 7th at Indian Springs. It is going to have a Ren Fest type feel to it. And then the one after that is October 21st at Stony Creek. They are looking for as many scopes and volunteers as they can get. I sent out an email about that. I'll send out another one.
Can you have scopes in the rooms?
Not only can steampunk them up, maybe, I don't know, but so the annual awards banquet this year is being held at the Ukrainian Cultural Center Monday, December 11th from 6 to 11. John Blum, a former president and probably every office in here, it will be the keynote speaker. Thanks again to Mark Hedzier for his efforts and for the banquet, and Dale Parton for securing John Blum. You can renew your membership online. Doesn't look like Adrian's here, so you're not doing that at the break, but online. We are looking for submissions for our 2024 calendar. So if you have anything, submit them to publications@warrenastro.org, and ALTV will get them, and we will have a calendar next year. We have elections coming up, I believe, next month it is, and we have several members that are being term limited out of their positions. Jeff McLeod said he'll be running for outreach. Right. What? Yeah. Don't do this. Marty will be running again for the observatory chair. I think he and Jeff swapped that position every for 3 years. So Dale Parkman will continue again as first VP. I'll be running again for president unless somebody wants the job. We need a new treasurer, secretary, and publications officer, although Dale Teamy said he was willing to continue as the editor of our newsletter. So the publications job might be pretty easy. Okay, officer reports. I don't have a whole lot except that of what I wrote in the newsletter. My granddaughter looked through a telescope for the first time, and I couldn't be more thrilled. And she actually saw the moon, and she also grabbed it and moved it around. And I said, "Can't do that." She got all upset. So pretty darn funny. But she's 3.5. She saw the moon, looked like that, and I knew she saw it. And I've seen 5 to 7 year olds not be able to do that. So I blame all of the cartoons that she watched with cartoon characters using telescopes. I've been watching it, yeah. So let's go. Officer reports. First VP, Dale Parton. What? Oh, pardon? You want to do that? Okay, let's do that. Bob, why don't you come up here really quick? We have a short announcement before we get into officer reports. Sorry, Dale.
Tim Burton asked me to announce this tonight. About a week ago, he called me and found out his wife has lung cancer and it's very bad. The doctor told him that it's a very aggressive, there's about a 5% survival rate. So unfortunately, doesn't look real good. He called me last night and said they took her out of the intensive care ward and put her in a regular hospital room. So at least that's one positive step, I guess. But anyway, keep her in your thoughts. So okay.
All right, thanks, Bob. All right, our first vice president, Dale Parton.
I'd like to say that I appreciate those who have been volunteering to give presentations. And we're booked up through March as far as full-length presentations. But starting in January, February, March, and April, I especially need short presentations, 10 or 15-minute presentations. So if you have something in mind, let me know. Even if you don't have it ready, you got plenty of time to work on it. I'll put you on the schedule so you got a specific date to present on. Okay? Thank you.
And about 5 different presentations come into my mind that I need to do. Yeah. All right, second VP, Jeff McLeod is going to be showing our really fancy new, what are these called?
Look at it. You can't see it. You should have been here. It was amazing.
Tall beams, 3 foot by like 8 foot tall. They're just gorgeous.
I don't know, it's part of the white area.
You move it and I'll talk. So, I did some material for my work, and they had these pollinators, and I'm like, where do these come from? So me and Dale Teamy worked together. He did all the hard work. I just kept telling him, "Need some little more for that." You make it just a tiny bit smaller. I know it'd be really annoying. But I think we got there, and they're gorgeous. So these will be assembling these. You mentioned the gas stack ratio. It's perfect. We also got trifolds purchased, so we have something physical to give people abstractly the beats. So they don't have to remember our website, they can just take that. I'm also encouraging them to take photos of this because it has some good information, but everything is in the trifold. They're beautiful as well. We got some tasting monitors. So we're gonna be looking good at starting to beach. And like Bob said, let any of the board members know we're trying to get a short list together of who's willing to volunteer and what capacity, so that we can kind of start figuring out who can help when, so that you maybe don't get stuck at the table all night. You can just do like a 2 or 3 hour shift and then enjoy the rest of the event. Just have to get enough people.
Yes, she received it. It's super busy. That's probably why you haven't heard back from her, but I know she got it. Thank you so much. And sent a smiley emoji.
That's funny.
All right, let's see, going back in time, our open house, a week and a half ago or so was really good. I don't know why I'm struggling to remember it. We had some heritage girls out there. We saw planets and nebula and all kinds of good stuff, so we had a good night. Yeah, you had some students out there.
I had some of my astronomers that show up.
So, and it was a good night, wasn't it? All those clear skies that I've been promising. I'm saying, I told you guys, can't be wrong forever. No, that's in the past. No one cares about that. The first thing were lackluster in my opinion, but I actually saw a really good handful of what I would call late proceedings recently. At least going in the right direction. The open house for this month is coinciding with astronomy at the beach, so you have to decide if you're going to be Brighton, yeah, Brighton, on Saturday, or if you're going to go to the observatory. Riyadh will be there, so it will be a normal open house, but most of us are going to be at astronomy at the beach, so just be aware. Boy, I think that's it. I'll remember as soon as I first.
I had a meeting on the board of GLAC last night. They were supposed to have it tonight, but everybody was having something else tonight. And I said, how about Sunday night? So we did it. Liam Finn, I believe in the Ford Club, has got NASA Glenn as an exhibitor at Astronomy at the Beach. They are bringing a 35-foot tall inflatable SLS, and they're going to have a scale model of the Orion capsule there. So I don't know. You guys can do the arm wrestling with there, but that was pretty cool, and I can't wait to meet them. He's going to go out there and meet them on Thursday, and they're getting a hotel room. And NASA Glenn, what he said is that NASA Glenn, they usually charge for these kind of things, but they had some discretionary funds, and since we are offering this event free to the public, they are putting their guys, sending them here and putting them up, and not charging us a penny for it. So that's cool. So, all right. Next officer, Adrian Bradley is not here. Treasurer, whatever we have in the bank is in our newsletter. I'm not sure what that is. Secretary Mark here. Yes, he's here. And wow. Oh, minutes are in the watch. Okay, Dale Teamy publication. The Wasp is in the Wasp. Yeah. So the news, our award-winning newsletter is up. Or would be award-winning newsletter editor? Or whatever. So, has anyone seen the comet in the morning sky? Has it been clear? Michigan, yeah, I thought so. Yeah, we were having this discussion. We were having this discussion at my house the other day. We were talking with my brother-in-law saying, hey, there's a comet in the sky. He's like, I brought up a picture. He's like, no way. I'm like, well, yeah, Michigan, no way. You're right. All right. So special interest group. Let's start with David Levy.
Well, thank you so much. I hope you can all hear me. I'm having a little difficulty hearing you, Bob.
Oh, you are?
I'm straining and I'm managing. Anyway, especially this quotation is especially relevant for those of you who might have seen Comet Nishimura in the last couple of nights. I saw it before before it got really bright as a very nice 7th magnitude blob, and it's just lovely. Anyway, the quotation is this. It's from actually something that I wrote. Our fondness for the stars has touched our souls. All of us, we all share the feeling of discovery. Whether the object we have found is new to all, or new only to us. The thrill penetrates our being as we try to describe, through drawings, photographs, or words, how we have been changed by the universe sharing a secret with us. Thank you very much, Bob, and back to you.
Thanks, David. All right. Is Riyadh here? Riyadh online. We have a double
Thank you.
star report.
Yes, actually, we've been doing a lot of double star observing, along with a few other objects that we've been looking at. And we've been pretty busy whenever it's been clear this summer. Hopefully, we'll continue with having clear skies. And at the next open house, I'll be there, and we'll have our usual list of objects to look at. So I hope everybody will show up. Thank you.
All righty. Thank you. Do we have any astronomy questions? No. Okay. All right. Well, with that, we're a little early here, but we can let's do observing reports. Anybody have any observing reports other than clouds? What I've been seeing.
Yes.
I think it is. I've seen a lot of pictures that are probably time exposures, but I you know what? I'll look it up. I'm not sure. They say that it is. Michigan. All right, so can we do a short presentation now? All righty.
Well, our first presenter, Jeff McLeod, is sort of well known in this organization. He's our vice president for the observatory, no less. Also a former president of this organization, and a regular at outreach events, as well as up here giving presentations. During his time at Wayne State University, he was a presenter in their planetarium while getting bachelor's degrees in both physics and astronomy. So he knows more than I do. He recently started employment in the aerospace sector, simulating missiles, and he says the rest is classified. Nowadays, most of his free time is spent working on a space flight simulator, a life-size recreation of a Gemini spacecraft you can sort of actually fly in. You need a pilot's license. His presentation tonight is called Fixing the Calendar Once and for All.
I do have one other announcement. There is an event, if you've not been to the Cranbrook Observatory, they have a plane wave telescope, and plane wave is actually kind of local to us. They're in Adrian, and they're having their second annual open house. It's going to be October 7th and 8th. It's a Saturday, Sunday, 11 to 6. We'll publicize it. But if you're interested, let someone know who will go to definitely publicize it.
I want while we're over.
Can you please be sure?
So,
They can hear you.
Yep.
I think the smallest and biggest. So.
They just-
That's fine. I'll just do the presentation. How do I open my essentially there? Not the PDF. Thank you. Just a moment. We got plenty of time. This is going to be a short and sweet one, so we're going to have a lot of social time for snacks. Do you guys remember my last short presentation? It was a challenge on locating lunar landing sites. This is an even loftier challenge. Oh, okay, we're good. Everyone can see everything? Yes? I can't see the internet people. Are they still okay? Oh, he can see the internet people. Okay. So, hmm, no. Let's see.
You can share the whole thing.
This one, whatever's easier. Here we go.
We're seeing as program, not the slideshow yet.
Oh. What do we have?
I don't know. We'll just keep picking one until they
There
can
we
see
go.
it. All right, you can see it?
Yep, we're there.
Ooh. Hmm. Okay, good enough. I'm just gonna look at that screen. All right. Not saying that the calendar's not fine. I'm just saying it's not perfect. Okay. Does anyone know how many days are in a year? Point 2477 something. We can do better. Okay. Just a quick history. We've had multiple calendars over the course of humanity. These are just a few. So the Mayan calendar was a very good. Lunar, solar, long. It lasted. Turn your phone on? Then we went to the Julian. That was okay. Still internet over here. Islamic calendar, Gregorian. That's the one we're on now. It's okay. There's buttons on the side. All right, we good? All right. Famously, they had to skip some days to get the Gregorian back on track, right? He had these leap years. So what I'm suggesting is the Warren calendar. Okay. So these leap days are the problem. And there's a couple of possible solutions. So if you're not familiar with a leap year, it's not just every 4 years, because there's not 365.25 days in a year. There's more decimal points. So the formula is if the year is divisible by 4, it's a leap year, unless it's evenly divisible by 100, then it's not a leap year. Unless it's also divisible by 400, then it is a leap year. That gets us the right ratios at the right decimal points to kind of keep the calendar good for quite some time, but over the long term, it's still not going to be good enough. We're going to have to add in other corrections, which is fine. However, wouldn't it be great if we could have a perfect 360-day year with perfect 30-day months? And I'm suggesting a 5-day week, 6 weeks a month, where you only work 3 days, right? Sounds good. All right. Yeah, 4-day work, 4-day work week, whatever. Okay. So we just have to move the earth a little bit. Shouldn't be, I'm talking less than 1%. Okay, so there's a couple ways we can do this. We can change the rotational speed of the earth. If we just add 21 minutes a day. That'll get us to 360. If we were lazy, we would maybe just take off that 0.2477, but that's still 365. What the 365? That's not good enough. Okay. So slowing the speed of the equator by just 25 kilometers an hour. It's going roughly what in kilometers? It's got to be like 1,400 something or 1,600, 16 something. It's a little bit. Okay, so the pro, you retain the length of the year. The con is we have to change the definition of a second to retain a 24-hour period. We don't want to have, we're trying to get rid of all these decimals, so we can't then have a date that's 24.21 hours. All right. The other thing we could do is change the orbit of the Earth. Now, changing the semi-major axis by 900,000 miles, that's less than 1%, will get us there. That's not much. 1%. How bad could that be? Changing the orbital speed by 525 kilometers a second. Or kilometers an hour. Now I'm thinking I didn't do the conversion. I did a back of the envelope calculation on how much this is going to take with conventional propellants, and I got a number that was 1,000 Saturn V first stages for about 1 billion years.
My question is, what if you're not break the Earth?
I will never break the Earth. Okay, so pros, retain the length of the day. Con, you hit 48 months faster. Okay, that's a problem for me. All right, so here's why orbital speed is the way to go. We can't screw with the moon, but the moon also has some problems. So if we want to slow the day down, it's easy. We speed the moon up, it gets farther away, we slow the day down. But if you move the moon farther away, you're reducing your solar eclipses, and I will not stand for losing eclipses. So we have to do something else. 29.5 days in the lunar cycle. I think we could fix that while we're at it, since we're going to be doing all this moving around, right? So let's make 12 perfect lunar cycles in a year. We'll shorten the year by 10.62 days or 64 days. This means that the day duration has to go up to get us back to 360. But the benefit of this, so that's the green orbit. But our orbit isn't perfectly circular, it's elliptical. So really, we only have to move one side of it, and we'll also get a perfectly circular orbit while we're at it, okay? So how? Lasers. Okay, we got all these asteroids on the asteroid belt. At some point, I'll crunch some numbers to see if we have enough. I'm assuming that there's some that we'll be able to use more than once. But this is actually something that they want to test on smaller scales. But you move small rocks that get close to larger rocks, that move those rocks, that move larger rocks. And eventually you kind of move something larger. I did another back of the envelope, doing a close flyby of like a 10-kilometer asteroid is producing millions of newtons of force. So you're still going to need a lot of these, but we have a lot of these, okay? So that's kind of my plan. The club's been around for 60 years. We can be around for another million, okay? We can do this. Yes. Do you want to move to a global time? I feel like that'll be weird. You'll be having breakfast at like 9 o'clock at night. Yeah. So is there anything else we can fix while we're at this? I'm not sure. The precession of the Earth's tilt, I feel, is a more complicated issue. When we fix our orbit, we're going to fix the equinoxes. They're not going to migrate the way that they do now. They still will migrate, but they'll migrate on the precessional period, not our weird orbital sloppiness. That'd be nice. And then the question for you guys is like, do we still want seasons? Should we put the Earth upright and just balance the sucker out? Or is that a bad idea? And then like, can you actually keep the precessional pointing on the North Star? That I don't know. I don't know if you can influence in the right ways without destroying our perfect orbit. Now, the perfect orbit, I think, is feasible. You're going to get perturbations and you're going to constantly, but once you get it there, it's just a flyby every couple of thousand years to put it right back on track. So anyway, that is my stupid, goofy presentation that me and some coworkers just went down a rabbit hole on. I was like, all right, well, I'm crunching these numbers and I'm going to tell it to somebody. So that is you people. Yes. I want someone who won't be in jail in 10 years. Question is, so the day is slowing down. So that is what we want if we move that orbit in. I have never heard anything about what's happening to Earth's orbit around the sun. If it's migrating. That's an astronomy question.
A couple of years on the sun. There's another map you can turn here. Who says the gravitational has to be constant? You trade a very.
I mean, if I could just move asteroids.
That's hard.
Well, you figure out where the knob is, and I'll turn it.
The amount of energy it would take to make it affect at all on the Earth's orbit is astronomical.
But in the asteroid belt is something like the mass of Mars, right? So you've got a tremendous amount of energy there. You use AI to figure out how it needs to move, and then you just start moving it. And you take it 10,000 years. Just let it go. You got all the energy in the world. Thank you. Yeah. See, if we would make fun of the other majors that wanted to like help the world, it's like, no, we want to solve goofy problems that don't exist.
All right, it is 7:30 and we are going to take our break, and let's say we meet at what, 8 o'clock for our feature presentation. All right, come on back in just about half an hour and for our feature presentation. We're all going to sit here and chat astronomy. Is the mic volume up?
No, it is. I think
Can
it's
hear you
talking to
fine.
the mic over there, so that's why they couldn't hear us. We just need to do it.
This is the origins. That's our observatory. What we kind of get, just the same here. We're Saturday of every month we're out there. So sometimes we do special. We were out there. That doesn't go in the dough. It rolls out of the field, and it's just, it's very similar to these other telescopes at the bottom of that banner. It's bigger than those. So those are like 12-inch, 14-inch. It's just like just something. It can be done. It can be done. I don't know. I still have scheduled time for that. I just need to know it actually is not massive. But I'm not paid to do that kind of stuff, so it's like there's so much time to waste on stupid problems. Seven pounds, like first one. Then grows out in Arbor, so there's sort of close. Yeah, I don't know what their it's like. I know 7 pounds typically kind of places. They're trying to make like uses, but there are some bluffs that are not too much out of the way here. Around and 7 pounds. It's worth its trades. I don't like it in the city. I know we all go operate certain. Yeah. I would say if you just have anything on our logo on it and say, hey, we're out there. Yeah, I'll try to. Yeah, no. No, still like. Some people love
It's the one that says newest. And we can show that's that one and the solar one. You have to make it dark, but that's a wide field I did up in the sun, and it was 5 degree by 7 degree mosaic. Took over 2 days for the Open Astronomy Club. Had a camp out up there in our meat park, and also a it was a star party, astronomy star party. So I did that over the 2 days. I did 4 hours each day. That's one. Yeah, that's pretty amazing. You get that's with an 80 millimeter scope. That's actually just backyard, the same thing with 80 millimeter. Go to the next one. This is what is really cool. Oh wow. Blow that up to blow up the screen. Here's the touch screen or
Doesn't look like it. Hold on a second.
you can see it pretty good on that screen behind you.
Stop. It's not zooming in.
This is on September 1st, my backyard. But this, you know, get the look behind you on the screen. Look at the resolution on it.
Lots of film. It's all over the place.
It's amazing. Yeah, I think you do that. That allows you to do that. Like it's
This is that Shedlowsky? This I think it's Shedlowsky. The RR. No, I thought this is ours. I thought one of them was touchscreen.
whatever.
That's gorgeous. That was taken from your.
No, the next one was the other one. It's with a triad filter. That's the same exact thing. Speaking of this was taken some mosaic. Go back to the other picture here. There. That was taken up in the thumb. That's a mosaic of a 7 degree by 5 degree. That's Gamma Cygnus. It's a sitter, star sitter. That was for total of 4 hours of exposures, 4 hours of 5-minute long exposure. 2 days. Oh yeah. Well, not really that faint, but it's just to me, it's just amazing the resolution. That's a little teeny thing. To me, the thing that's cool thing about this, every single white dot is a star. You know, look at through the area like that, just amazing. You know, the number of stars in it.
What kind of lens is this?
That's my 80 millimeter refractor, but it's a mosaic. It's a
Ceramic,
yeah panel. And to show them the solar one. And that's a solar. Like you see it better on the screen there. But see all the prominence is, and when you look at the resolution, you don't see it different. You get on your laptop, blow it up in the laptop. It's a resolution. It's amazing. Oh yeah, that's 4,000 exposures of video frames. 2,000 of them for this part, the chromosphere. Another 2,000 for this. Then the software goes through all these 4,000 pictures, picks out 15% the sharpness and contrast, because even though it's just a fraction of a second, there's still a huge difference in the seeing and everything. And then it lines them all up, and then you use Photoshop, and this part you put onto one layer, the prominence you put on another layer. So you cut one part out, put on top of the other one. So there's such a wide difference between the brightness of that versus these. So that's the way you can do it. Well, it is. I'm doing. I'm doing it in next year. He's got me scheduled for that. Anyway, but when things start up, you can tell people or cut the license, but they can show it to them later at the end of the meeting or whatever. See those two. I'll get this thing back later. Okay.
Nobody knows about us. Sure. Yeah.
Right. 8-minute warning.
Did I ever see two or? Yeah, is it on there or
Yeah.
the video?
I don't know which video you're talking about. Yes.
It'll take too long to dig for it. I have. I don't know where I put it. Yeah, video. That's pretty. One of the guys worked for. That's what I'm looking at. Yeah. Oh, what's the name? Yeah. Oh, here you go. Was here. We haven't picked anything out.
Is this on internet somewhere?
Pardon me?
Is this on? Like
I
YouTube?
think it's on Facebook right now. I sent the link to my wife. She watched it. I didn't send her the video. So I have a link for it somewhere.
Yeah, you can just put it on a YouTube channel.
I think what we want to do is we want to have them edit like a couple words. They call this the Warren Astronomical Club, not science. And there's one other word, Stargate Observatory. I think they messed up the name of that. So, all right. So we're ready to get started here.
Okay. I stopped sharing, so we're good.
All right, so welcome back. Again, this is the Warren Astronomical Society, and we are going to have our feature presentation. So I'll have our introduce our speaker.
Thank you, Bob. Can you hear me? Wow. Our speaker tonight is Jim Shedlowsky, longtime member of this organization, former treasurer of this society, and rockabilly legend. So he claims. Graduated from the University of Michigan back in 1960 with a degree in engineering physics. Worked for 36 years as a vehicle development engineering manager. In his spare time, he wrote and recorded music for Epic and Roulette Records. It's one of the Ski brothers. Jim's astronomical interests include observation and outreach. He owns several telescopes. So do I. I wonder which one of us has more. I'm wife limited in how many I can have. In recent years, his passion for astronomical history and technology has become a major thing in his life. He is a member of the McMath-Hulbert Astronomical Society and has visited a number of major observatories. He and his wife winter in Mesa, Arizona, with some really nice dark skies, I'm sure. And he participates in activities of the East Valley Astronomy Club. I assume that's in Arizona. His topic tonight is searching for the dark universe. Jim? Okay. Oh, yeah. We're getting there. Good to be back here live, by the way. Always nice to see a live audience rather than that little camera. We're looking for a password here now. It's always good to have somebody that knows what they're doing up here, manipulating the laptops. I can see some of you old timers out there. While we're waiting here, and some of you might have noticed that I'm walking around too good. I've had several back surgeries, and looks like I'm going to be using a cane for the rest of my days. So, since I just turned 86 last February, I've resigned myself not to be going out to Arizona this year.
probably, I found out I can't hike anymore and do some other activities. So I can play golf back here, so. Okay, let's see if we can get the slideshow up here. Turn this side. Looks like no, I'm not using it all. There we go. Oops, no, we've got that thing. I need my script. No, with the slideshow. You had it up before.
Is this one?
Oh, there's another screen that has a presentation mode where I can read script and stuff like that. I guess this might work, I guess, but this is hooked up to an HDMI thing, or you're hooked into another network with it, correct?
Yes.
Okay.
This was the document. This is having the
Okay, so I can't do the format that I had before. I'll try to. Can I get rid of this?
Yeah.
Yeah. So now we got to get back to where we were a moment.
screen.
I can read this, but no, the slides are not. You have the slides. You go to the slideshow again, I can see. And you go the current slide. Oops, gotta go back one.
Do you know where this presentation
I guess I'm gonna do it this way. Oh, we gotta get the. We don't have. Okay. Now, try going from the current slide. Now we're back to.
I'm not sharing the screen.
Pardon?
I'm not sharing the screen.
No, I know I'm not. I'm sure.
You can share the screen.
Wish I knew some good jokes about IT stuff.
Bottom right, you'll see a slideshow icon. Yeah. Right next to the slide, right next to it, right there. Hit it.
We've got the right slide up here now, but we don't have the script. That's the problem. Trying to do it. We had what you just had it. Just now we need this one here and the other one there. I think the problem we have is we've got another laptop here that's doing the broadcast, I guess. I'm not sure what's. I had it hooked up at home with just an HDMI cable to my computer, and that allows you to do the presentation mode and slides up here. And,
Can you ad lib it?
no.
Always on top of that, with it from the beginning.
We
We had it running here earlier with the laptop just hooked up to the HDMI cable, but I don't know if we can. There we go. There we go. We got, this is what we need for me. Now we need something for them. I think what we've got is this second computer, which is overriding the first computer here.
I can't hear you real well. You want to presenter view? Yeah, that.
Okay. Looks like we've got it going. Knock on wood. Good evening, ladies and gentlemen. Welcome to a presentation which I prepared 3 years ago and have recently updated. I picked up on a theme that I covered some 12 years ago entitled The Way We Found the Universe. That presentation covered the exciting period in the early 1900s when Einstein and Hubble revolutionized our understanding of the universe, and helped out by the likes of Henrietta Leavitt, Vesto Slipher, George Lemaitre, and others, formulated the, at that time, revolutionary Big Bang theory of an expanding universe with its island galaxies. Tonight's topic came to my attention when in a tiny library in Roscommon, Michigan, where my wife and I hang out, I found this slim volume, which caught my attention with a statement in its introduction. Quote, most of the articles gathered in this anthology were selected to capture the revolution that has shaken cosmology and our understanding of the universe in the last few years. So with a statement like that, and my cursory awareness of such things as dark matter and dark energy, my curiosity was aroused. This book's compilation of articles by noted astronomers and physicists essentially provided a primer on the controversies that have been going on in astronomy for the last few decades, the most momentous since the proposal of the Big Bang theory in the 1920s and 30s. Let me see if I can find my pointer here. Can you hear me out there all right? This revolution on the subject, including one, excuse me, I've done some further researches here. That these are some of the books that I found, including one appropriately titled "We Have No Idea." And being cautioned by Dr. Parton that this would be a risky presentation topic, I decided to proceed with researching what has become for me a fascinating ongoing chapter in the history of science. I hope you'll enjoy my attempt to summarize for you the current turmoil going on in our understanding of the universe. In searching for an appropriate title, I was tempted by numerous articles in various publications, or by the title of a conference that I attended at the University of Arizona's Stewart Observatory in Tucson recently, which implied a crisis, turmoil, or tension within the cosmology community. I finally settled on the less dramatic phrase above, which suggests that much of this controversy has been brought about by the largely unfulfilled quest for the nature and properties of two mysterious quantities, which have been aptly named dark matter and dark energy. I briefly considered making the title of this Dark Energy and Dark Matter for Dummies. So I hope I've got it to a level that we can converse on. My presentation then will review the Standard Model of Cosmology, sometimes called the Concordance Cosmological Model, and recent revolutionary revisionary thinkings about it. Let us first look at the general structure of the universe as it is now defined or described by the Standard Model of Cosmology. It is some 13.8 billion years old, and its observable diameter spans 93 billion light years. It contains over 10 million galaxies, each with from 10 million to 1 trillion stars. That's 10 to the 24th stars, or more than all the grains of sand on Earth. These galaxies are organized into clusters and finally superclusters, the largest gravity-controlled structures in the universe. Of the overall content of the universe, only 4.9% is ordinary matter, which we can detect directly, that we can see with our telescopes, with the rest consisting of 26.8% dark matter and 68.3% dark energy, both of which we know very little about, and which we will explore later in the presentation. Since this standard model has been developed over the years with certain assumptions and theories, and then supported with ongoing observations and data, I'd now like to briefly review the history of our understanding of the universe as it has developed over the centuries in the Western world, from the early Greek philosophers through Copernicus, Galileo, Newton, Herschel, Hale, Einstein, and Hubble, and finally to today. The earliest models of the universe come from the ancient Greek philosophers and then later the Arabian astronomers, and are represented by Ptolemy's model of the universe, which were preserved in his book, the Almagest, which presented the Earth as the center of the universe within a sphere of fixed stars at a distance of 20,000 times that of the Earth radius. This book was the authoritative text on astronomy for hundreds of years, and it was almost universally accepted until the scientific revolution of the 16th and 17th century, when the simpler Copernican sun-centered model eventually took its place, with additional contributions from the likes of Galileo, Kepler, and finally Isaac Newton, who with his mathematical treatment of the laws of motion and gravity, finally allowed a somewhat modern perspective on the solar system and its galactic neighborhood. Later in the 18th and 19th century, as the development of telescopes and other technologies progressed, the size, content, and extent of the universe began to be questioned, as is illustrated by this slide, showing William Herschel's 1811 chart of his observations of nebula and the distribution of them across the sky, and suggestions that they were something other than stars, along with Lord Ross's famous hand-drawn 1845 sketch of N51, the Whirlpool Nebula Galaxy. These hints of a larger and more complex universe were suggested and further advanced later in the 19th century with the arrival of photography, as with Isaac Roberts' famous photo of the Andromeda Nebula from 1888. Still, at the end of the 19th century, our view of the universe was somewhat parochial in nature. The accepted model maintained that the Milky Way, our home, was the universe, and that it was about 30,000 light years in diameter, with the solar system in the center. It further suggested that the common age of the sun, the Milky Way, and the universe was some 20 to 40 million years, and that the mysterious spiral nebula that were then starting to be detected were other planetary systems in the Milky Way that were emerging, just as our own solar system had. Other viewpoints existed, but were not mainstream until the first part of the 20th century, when a number of significant developments by individuals caused a momentous change in the way we understand the modern universe. This revolution in our concept of the cosmos, which I have classified as the early modern version, involved a number of significant steps over a 15-year period, which combined to redefine the universe as we knew it. In 1912, Henrietta Leavitt's brilliant insight regarding the use of Cepheid variable stars as yardsticks or standard candles for measuring cosmological distances, coupled with Vester Slipher's 1914 groundbreaking use of Doppler spectroscopy to discover the recessional speed of spiral nebula was many times greater than that of any star, combined to give Edwin Hubble the tools that enabled him in 1925 to settle the 1920 Great Debate by establishing definitively that spiral nebula were in fact internal or external island galaxies. And then by 1929 to proclaim that the universe was expanding as governed by what we now know as Hubble's law. All of this was put into a revolutionary new mathematical framework in 1915 by Albert Einstein with his general theory of relativity. And then in 1917, Einstein published a paper entitled, quote, Cosmological Considerations in the General Theory of Relativity, in which he attempted to mathematically describe a universe which was static, as that was a common assumption of the pre-Hubble era. To do so, he was forced to introduce a term in his equations called the cosmological constant, or a fudge factor, to assure that gravitational stability in his space-time universe. Einstein was challenged in this static universe assumption by several mathematician contemporaries. In 1927, an astronomer, mathematician, and a priest named George Lemaitre reanalyzed the Einstein equations of general relativity without the static universe assumption and found that it matched the expansion as announced by Hubble several years later. In 1931, this formed this, go back here. Get it, yeah. This forced this the Lemaitre and Lemaitre's reanalyzation of Einstein's equations forced Einstein to recant, embrace the expanding universe, and admit that the cosmological constant was the biggest blunder of my life. As significant as Lemaitre's use of Einstein's mathematics to describe the dynamics of Hubble's expanding universe was his insight that this implied that in the past, it must have been smaller. And further, that at some point there had to be a beginning or an origin of the universe, a primeval atom that expanded to generate everything in today's universe. He referred to this concept, Lemaitre referred to this concept as the day without yesterday. The expanding universe theory had been born, although it would be 20 years later, in 1949, before the British astronomer Fred Hoyle coined the name the Big Bang in a critical put-down of Lemaitre's theory. In spite of the acceptance of Einstein's mathematics as interpreted by Lemaitre's model and verification by Hubble's measurements, the Big Bang theory did not immediately gain wide acceptance in the astronomy community. Critics pointed out that using Hubble's data for expansion, the universe would be only 1.8 to 2 billion years old, much too young for the older stars, known to be up to 10 billion years old, or even the geological age of the Earth. Others, conditioned to an eternal universe and cautious about potential religious overtones, had a difficult time accepting any notion of a creation date. Several alternative scenarios were presented to account for Hubble's redshift measurements, but of these, only one received serious considerations over the ensuing decades. This was the steady state theory, as conceived of and championed by Fred Hoyle in the mid-40s. Hoyle's theory, which described an eternal and ever-expanding and continuously creating universe, which would accommodate Hubble's law and an interpretation of Einstein's general relativity, along with some observational evidences. Its long-term resiliency was evidenced by a survey conducted in 1959 by the Science Newsletter, which polled prominent astronomers as to their position on the theories. Of these experts, 33% favored the Big Bang, 24% preferred the steady state, and 29% were undecided or thought that both models were wrong. Among the early proponents of the Big Bang Theory were many in the physics community who were busy exploring the revelations of the burgeoning field of nucleosynthesis. Einstein's most famous equation, what is it? Einstein's most famous equation. Come on. E equals mc, right? Had finally conceived of a process for explaining the enormous energy produced by the sun and other stars. Developing the equations and conditions for the transforming of hydrogen into helium led George Gamow and his associates to calculate the production ratio of these light elements under the conditions that would have existed in the Big Bang era. This ratio matched the measured ratio in today's universe, providing strong support for the Big Bang version of cosmology. Gamow went further on to predict that there should be a remnant radiation field that might be detectable, and that it should have a signature redshift microwave wavelength with a temperature of around 5 degrees Kelvin. That this prediction, some 17 years before the cosmic microwave background radiation was actually observed, was ignored, was a monumental oversight at that time. Due to the primitive status of microwave technology in 1948 and the inability of Gamow to convince their colleague, Gamow and his associates to convince their colleagues of its significance. Throughout the 50s and early 60s, the debate between the Big Bang Theory and the steady state communities raged on, with Hoyle revamping his eternal steady state universe theory and inadvertently solving a problem that had stymied the Big Bangers. When in 1957, he and his colleagues published a landmark paper, which explained the synthesis of the heavier elements as products of stellar fusion and end-of-life explosions like supernova and processes not related to the birth of the universe. Particle physics and quantum mechanics had now become a serious partner of astronomy and integrated into cosmology. It would be 1965 when the next major chapter in the confirmation of the Big Bang Theory's acceptance by the scientific community occurred. As mentioned earlier, in 1948, George Gamow and company had predicted an artifactic radiation from the Big Bang, which they call recombination. Their calculations had been based on the pressures, temperatures, and densities in the very early universe, as prescribed by running the expanding universe clock backwards. They had predicted that about 300,000 years after the Big Bang, the temperature of the universe would have cooled to about 3,000 degrees Kelvin, 5,900 degrees Fahrenheit, which would have allowed the free electrons to combine with the nuclei, forming the very first atoms, and would have emitted a sea of light which might still be detectable. They had even predicted its microwave wavelength or frequency and temperature and calculated a redshift temperature measurement of about 5 degrees Kelvin today. In early 1964, Arno Penzias and Robert Wilson, two astronomers working for Bell Laboratory and preparing a large microwave antenna to do a sky survey of radio sources, were plagued by a persistent, unwanted background noise in their system that seemed to come from every direction. After months of efforts to no avail to reduce or eliminate this noise, a casual exchange between Penzias and another astronomer at an astronomy conference led to one of the greatest discoveries in cosmological history. Further measurements and consultations confirmed that the noise problem they had been struggling with so long was indeed the cosmic background radiation, which had been predicted by George Gamow 17 years earlier as an essential part of the Big Bang, and not explainable by Hoyle's steady-state universe. Penzias and Wilson would be awarded the Nobel Prize for Physics in 1978 for their discovery. A further property of this baby picture of the universe was the expectation that if looked at in more detail, there might be fluctuations in the radiation that could reveal additional information about the early universe. Over a period of more than 2 decades, and this effort was undertaken by many researchers, among them George Smoot. After many failures using high-altitude balloons and U-2 aircraft to minimize the effects of atmospheric water vapor, in 1992, Smoot was part of a team that was successful in using the COBE satellite, C-O-B-E satellite, to confirm its uniformity across the sky and the universe, but also to measure tiny temperature variations of 1 part in 100,000, or 1/1000th of a degree, in the cosmic microwave background radiation, which had major implications in our understanding of the early universe and its age, composition, and structure. For this analysis, Smoot was awarded the Nobel Prize in Physics in 2006. The importance of the accurate measurement of the cosmic microwave background radiation was of such significance that several follow-up satellite missions have followed COBE, each of which have improved the resolution of the images and added further information to this ongoing primary contributor to the description of the Big Bang universe. The current measurements of the cosmic microwave background radiation are the most precisely measured spectrum in nature, with a redshift temperature of 2.7245448 above absolute zero, and fluctuations of 100,000ths of a degree Kelvin. This gives an angular resolution of about 1/12 of a degree of arc. These measurements, combined with other measures and incorporated into other aspects of the analysis of the Standard Model of Cosmology, such as particle physics and quantum mechanics and so on, and additional observations of galactic dynamics and contents, finally secured the position of the Big Bang theory as the dominant description of the early universe among the astrophysics community. Some of the things this tells us is that our universe is 13.82 billion years old and was inflated from a singularity which imprinted its signature some 379,000 years later as the cosmic microwave background radiation, when the universe had cooled to 3,000 degrees Kelvin, which allowed the so-called recombination of electrons to join the hydrogen-helium nuclear plasma to form the first atoms. This allowed light to radiate throughout the expanding universe for the first time. The pattern of the minute temperature variations in the cosmic microwave background radiation is believed to describe the structure of and the distribution of mass and energy in today's universe. Essentially, the cosmic microwave background radiation had ended the controversy between the Big Bang and the steady-state theories, but had opened new controversies in the Standard Model of Cosmology. Questions of how fluctuations in space-time had generated the enormous disturbance, energy, and mass that became the Big Bang universe from a singularity had by now become a mystery in the domain of particle physics and quantum mechanics, and some would say in philosophy or religion. That continues to the present. Just as vexing was how this singularity expanded to become the cosmic background radiation detected as microwave signals 13.78 billion years later. The cosmic microwave background radiation presents a photograph of the universe when it was 378,000 years old that we can look back to and make ever more detailed observations of with sophisticated telescopes and instruments at various wavelengths. But it also presents a barrier beyond which we cannot gather electromagnetic data. The timeline of events surrounding the Big Bang event as currently postulated and accepted by the astrophysics community are as follows. A quantum fluctuation in the balance of matter and antimatter in space-time occurred at the beginning. That was the Big Bang itself. Immediately followed by a period of time known as inflation, lasting some 10 to the minus 35th seconds, during which the universe expanded to some 10 to the 25th times, faster than the speed of light, to the diameter of about 1 centimeter, during which time it achieved a high degree of homogeneity. After this amazing expansion, the universe continued to expand at about the current Hubble rate for about 380,000 years, to a radius of 42 million light years in radius. All the while cooling to a temperature of about 33,000 degrees Kelvin, at which temperature the first atoms formed and the universe became transparent and formed the baby picture of the universe that we now know as the cosmic microwave background radiation. From that, I had a footnote here that using that scenario at 1 second after the Big Bang, 1 second after the Big Bang, the universe was about 10 light years in diameter. From that inflation epoch or era, the universe expansion has continued for some 13.8 billion years, that's the visible universe, and now spans some 93 billion light years, usually known as the observable universe. The description of the origin, the history, and the development of the universe was the accepted version toward the end of the 20th century. The inflation theory had its critics, but since it addressed basic issues with respect to the overall Big Bang theory and was based on sound particle physics and quantum mechanic principles, it was the mainstream thinking. However, other issues had arisen in the observational astronomy arena. The observed dynamics of the galaxies and galaxy clusters were exhibiting unusual anomalies. They were not moving as Newton and Einstein had dictated. In 1980, an important paper by Vera Rubin and Kent Ford reviewed the results of 10 years of observations of the rotation of galaxies, which revealed that the velocity of stars and hydrogen gas was fairly constant, as measured radially from the center, instead of dropping off as it should have, if governed by Kepler's law, with the visible mass of the galaxy. Some invisible, attractive gravitational force was present. These graphs became known as Rubin's flat curves, and she spent much of her remaining career studying this phenomenon. In 1933, this same effect had been observed by Fritz Zwicky, the mad astronomer, when observing the Comet galaxy cluster, where to explain its motions gravitationally, you would require 400 times more mass than was visible. He called this missing mass donkal materiae, or dark matter. Zwicky never followed up on his discovery, but the term dark matter stuck, and Rubin's work with it would have a profound impact on cosmology going forward. Rubin's work revealed that most galaxies contain 5 to 6 times as much of this dark matter and its gravitational influence as visible matter. And this magnitude of increase in gravitation caused the cosmology community to take notice. Something big was out there and we couldn't see it. Its mysterious properties of not interacting with any electromagnetic radiation or light meant that direct observations were impossible. However, by using its gravitational effects by the early 1990s, dark matter's influence had been discovered throughout the universe in halos that surrounded galaxies and galaxy clusters. And using gravitational lensing and computing algorithms to map dark matter, it was possible to visualize it, as is shown in this reconstruction, where dark matter is shown as a light blue haze surrounding the visible elements in this galaxy cluster. Or next slide here. Further refinements have resulted in spectacular images showing the collisions of galaxy clusters, including this spectacular view of the so-called bullet cluster, which clearly reveals how the ordinary matter, which is shown in pink and mostly gaseous in nature, reacts to the collision as opposed to the dark matter, which is shown in blue. More significantly, in 2007, the Cosmos survey, using images from a number of observatories, including the largest survey ever from Hubble, which was 575 images over 1,000 hours of observations from the Hubble, produced this 3D map of dark matter clumping in the area of the sky, in an area of the sky that was 9 times that of the full moon, or some 5 times the volume of our home Virgo supercluster. And going back in time halfway to the Big Bang. This study indicates that normal matter accumulates along paths with the densest concentrations of dark matter, and dark matter clumping probably provides the seeds for the formation of galaxies and clusters. Quantitative survey measurements calculated that fully 85% of the mass in the universe was made up of this stuff that we can't see. Dark matter was real. It was important. It exerted gravity, and we didn't know what it was. And this really got the attention of the particle physicists. And with the increase of total mass in the universe by a whopping 85%, could astronomers explain the effect on the expansion rate of the universe from this huge increase in its known gravity? By the mid-1980s, one thing was fairly certain about the expansion of the universe. It might have enough mass density to stop its expansion and recollapse, the big crunch. Or it might have so little density that it would never stop expanding, the big chill. But gravity was certain to slow down the expansion as time went on. Granted, the slowing had not been observed, but theoretically, the universe is full of matter, and the attractive force of gravity, now multiplied times 6, pulls all matter together. By this time, there was a feeling both in the astronomy and the physics communities in the need to have a better understanding of the expansion rate of the universe over the time or over the life of the universe. We needed to look back farther in time to see how the expansion rate had behaved when the universe was much younger, and we needed to look much deeper in space. Recall that it was Edwin Hubble who in 1929 first measured and announced to the world that the universe was expanding. He accomplished this by measuring the distance and recessional velocities of 24 galaxies out to a distance of about 2 megaparsecs, or about 6.6 million light years. By using Henrietta Leavitt's Cepheid's variable stars as standard candles for distance, and Vesto Slipher's Doppler redshift measurements for velocities. While Hubble's feat established the expanding universe and created Hubble's law and the Hubble constant, it was quite inaccurate and limited to the relatively short cosmological distances which Cepheid variable stars were observable, about 60 million light years. The inaccuracies were reduced by later observations and techniques, but the distant limitations imposed by the Cepheid variable's brilliance remained in place into the early 1990s. The Hubble constant, h sub o, which is the slope of the distance versus the velocity plot of deep sky objects, had become the standard for measuring the expansion of the universe and other related parameters. For example, the age of the universe is 1 over h sub o, or the reciprocal of the Hubble constant. As originally defined by Hubble, its value was about 500 kilometers per second per microparsec, or megaparsec, which indicated a universe that was only 2 billion years old, younger than the age of the Earth. By 1990, when we could still barely measure distances outside of our own home Virgo galaxy cluster, which is about 7.5 million light years, the Hubble constant had been revised down to somewhere between 50 and 100, which gave an age of the universe of about 10 to 20 billion years, with still a great deal of uncertainty. With the precision satellite measurements of the cosmic microwave background radiation beginning in 1992 with the COBE mission, an independent measure of dating the age of the universe and thus deriving the Hubble constant became available. Later, with the more precision of the WMAP satellite and the Planck satellite in 2009, the Hubble constant was inferred from the minute cosmic background radiation temperature variations using assumptions about dark matter, neutrinos, and other substances. And this calculated value for the Hubble constant was within the tolerances of the direct observational values. But there was general agreement that with the revelations brought on by the discovery of dark matter, it was about time to pin down the value of h sub o, or the Hubble constant, once and for all, and to see if it had changed in the last 30 or 13 billion years. Was the Hubble constant or not? A new standard candle was needed, which was much brighter than the Cepheids used by Hubble and his successors. There was a general consensus that the best candidates for a Cepheid class standard candle that was visible over much greater distance would be supernova, except for two problems. Number one, they're very rare and unpredictable. And number two, their luminosity standardization was questionable. Supernova are rare. They occur on the average about once in a century in our own galaxy, and their occurrence is not predictable. Fortunately, there are millions of galaxies out there to monitor. However, since a supernova event is transient, lasting only a couple of months, and unpredictable, detection, which can be accomplished by a relatively modest telescope, and then follow up by measurements, which requires more detailed measurements by larger telescopes, becomes a complex logistical problem of managing the allocation of scarce astronomy technical resources, that is, observing time, with short lead times and durations. In 1998, the National Science Foundation authorized $6 million for the establishment of the Center for Particle Astrophysics at the University of California in Berkeley, to recognize the connection of the very small with the very large in physics versus astronomy world. The name of this agency might well have been the, quote, Center for Dark Matter, end of quote, as this was the motivation for its creation, along with the revelations from the cosmic microwave background radiation. One of the first initiatives of this new organization was to create a group to look deeper into the universe, further into the past, and try to see how much of its expansion rate had been slowed down by all of this new gravity from dark matter. A small group of physicists and grad students at Berkeley had been dabbling in an automated search and find system using a 30-inch telescope near campus and new computer technology that by 1987 had bagged 4 supernovas in nearby galaxies. This demonstration proved that their system could potentially automatically find more distant supernova in quantities, given more resources. With the creation of the Center for Particle Astrophysics, this small group was given the resources and a formal charge to measure the expansion rate of the early universe using supernova as a new standard candle. With a name, the Berkeley Automated Supernova Search, or they called it the BASS team, a formal assignment and expanded resources, Saul Perlmutter and his associates began their efforts to develop an automated system to identify and classify deep space supernova and to validate a standard luminosity for them. By August 1992, they had found their first deep space nova with a record redshift indicating it to be from about 4.7 billion years ago. Those physics guys had actually figured out how to do astronomy. They had developed what they called the batch method, whereby they would perform a wide field survey of a given region of the sky with as many as 100 observations over a couple of nights, encompassing tens of thousands of galaxies. Then 2.5 or 3 weeks later, they would resurvey the same region using a high-speed digital scanning research system to compare each pair of photographs. They could then quickly identify supernova candidates, which they could immediately then send on to larger observatories, which had been scheduled ahead of time for detailed photometric and spectroscopic studies. This method guaranteed them to find at least a few supernovae in each batch, and they could deliver supernova on schedule. Second problem of luminosity standardization was at first a major problem, in that the supernova 1As, which had been chosen as the most promising, seemed to have an unacceptable variability in luminosity. This problem was solved in 1993 by an astronomer named Mark Phillips in an almost Henrietta Leavitt fashion. He had been studying the light curves of 9 nearby known supernova 1As and noticed that the shallower the descending slope was, the brighter was the intrinsic luminosity. Thus, while supernovas 1As did not have a standard luminosity, they could be calibrated. They could therefore be used as standard candles, bright enough to measure distances and velocities back to the earliest period of the universe. These supernovas 1As, by the way, have a luminosity which allows distant measurements some 500 times that of Cepheid variables. By this time, this is 1994 now, the astronomers had formed their own supernova search group named the High Z team, or the High Redshift team, 6 years behind the physicists, but with hopes of catching up with their, quote, superior knowledge of supernova and all things astronomical. The High Z team was comprised of more than a dozen astronomers from 7 observatories and institutions and led by Brian Schmidt. Using their own version of the batch system and having access to a wide variety of telescopes, they quickly began bagging supernovas of their own. So by the mid-1990s, there was a rigorous competition going on between the physics community led by Saul Perlmutter and the astronomers led by Brian Schmidt to discover how much the expansion of the universe was slowing down because of this huge increase in gravity from dark matter. By early 1996, the two teams were able to deliver supernova on any scheduled date with a kind of confidence that allowed them to convince Robert Williams, who was the director of the Hubble Space Telescope at that time, to use his discretionary time on the Hubble, like that which delivered the Hubble deep field images. But to use his discretionary time to use the Hubble's high resolution, precision photometry, and spectroscopy on a sampling of very deep space supernova to augment their growing database. In the autumn of 1997, each team was busy analyzing their limited data sets, bolstered by several Hubble high-speed or high-precision measurements in their own unique fashion to find a preliminary answer as to how much the universe was slowing down due to its increased dark mass density. By the spring of 1998, each team was interested in reporting their findings as soon as possible in an effort to be first. Both teams reached a similar result almost simultaneously, but there was a problem. The data revealed that the expansion rate was not slowing down as it was presumed, but was increasing, suggesting that the increased mass density from dark matter was being canceled by some anti-gravity repulsive force. The physics or the VAST team's analysis revealed that the mass density required to slow down the expansion of the universe was not only inactive or inadequate, but it was deficient by 40%. The astronomers, the high Z teams, completely independent preliminary results came in a week later at 36% too low of mass density. These unexpected, amazing, and virtually identical results from two rival, competing, and completely independent scientific groups caused a major upheaval in cosmology that continues to the present. Preliminary conclusions have been reinforced and refined by much more data. The mysterious anti-gravity force has been given the name dark energy, and Saul Perlmutter and Brian Schmidt shared the 2011 Nobel Prize in Physics for its discovery, after a decade-long feud about who was first. Dark energy, like dark matter, cannot be directly observed, but it can be inferred and therefore measured by its anti-gravitational effects on the visible large-scale matter in the universe. The new Standard Model of Cosmology since 1998 postulates that on a large scale, on the large scale dynamics and expansion of the universe is controlled by a combination of gravity from matter, both regular and dark matter, and dark energy. The currently accepted values of about 5% regular matter, 27% dark matter, and 68% dark energy suggest that the expansion of the early universe was controlled by gravity and was slowing down until about 7 billion years ago, when dark energy's influence began to give us the accelerated expansion we see today. These little markers I put on this slide kind of indicate about 7 billion years ago. So the universe was expanding slower back here, but faster up here because of dark matter and dark energy. So our knowledge of the universe as we now understand it, or don't quite understand it, has been evolved over the last 100 years through a series of significant steps, starting with Hubble, Einstein, and Lemaitre's expanding universe and Big Bang theory. Then came Gamow and Hoyle's postulation of the creation of elements by marrying the laws of particle physics and quantum mechanics to astronomical dynamics. This led to the accidental discovery of the cosmic background radiation with its subsequent exquisite measurements, allowing the detailed modeling of the birth of the universe. The science of astrophysics had come of age. Then came the last 50 years of major and in some ways speculative, confusing, and unexpected discoveries which have shaken the astrophysics world. First came Vera Rubin's documentation of a new source of gravitational influence, which doesn't interact with light or radiation and dominates regular matter by a significant amount. We now call this material or quantity dark matter. Dark matter's presence created a new challenge to the astronomy and particle physics, and together the astrophysics communities. How did all this dark matter affect the dynamics of the universe? The quest for the answer to that question became an interesting competition between astronomy and physics communities, which resulted in a minor revolution in astronomical measurement technology, but even more important, the discovery of yet another element in the control of the expansion of the universe. This time, the quantity was a repulsive force, pervasive in the universe and amounts greater than that of all the gravitational attractive forces combined. We now call this entity dark energy. With revelations from the cosmic microwave back radiation, the theory of inflation, and now dark matter and dark energy, the world of astrophysics has been revolutionized and is in a significant state of flux. While our understanding of the universe, its past, present, and future is much advanced over what it was 100 or even 50 years ago, we now have a number of major questions which remain to be answered concerning this dark universe. Some of these questions are: 1, what is dark matter? It may be as yet some undiscovered subatomic particle or not. Since it doesn't interact with electromagnetic radiation, we can't measure it directly. We have no idea what it is. Second, what is dark energy? It seems to be detectable only on large scales, galactic and larger. It's repulsive, and that's about all we know about it. Number 3, is the Hubble constant a constant? And what is its true value? The accepted cosmic microwave background radiation calculated value of 67.4 is not consistent with the directly measured value of 74. Those two numbers, by the way, would give you an age of the universe of either 3.8 billion or 3.3 billion. Only a half a billion years old difference. So. 4, what is the mechanism for inflation? What field or force could have caused the faster than speed of light expansion of the very early universe? Is there such a thing as an inflaton? Number 5, is the universe homogeneous and isotropic on the largest scales? And finally, what came before the Big Bang? These and many other questions are currently hot topics in today's study of the universe and are commanding worldwide efforts to resolve them. These questions are the justification for billions of dollars being spent on programs like the LSST, Rubin Observatory, or the James Webb Space Telescopes. To quote the title of one of the books I mentioned earlier, the answer to these questions is, we have no idea. But perhaps soon we will. I'd like to conclude by quoting some closing remarks from a 2016 book by Stuart Clark entitled The Unknown Universe, one of my references. He said, quote, today all our wishes would be granted if we could directly measure dark matter and dark energy, and that there are only two possibilities, either dark matter and dark energy are real, and these vast reservoirs of matter and energy are just waiting to be found, or we have to radically rethink fundamental physics. And finally, either way, we live in an unknown universe. And further, we live in an exciting time for cosmology. And now, if I can, I'd like to add a final verse to a Don McLean song that I first rewrote in 2008 for a presentation from this very podium entitled Astronomic Metrics. And then I added another verse in 2011 for a presentation entitled The Way We Found the Universe. And here's my finale version of Starry, Starry Night. You guys know the melody, so join me in the singing. Can you hear me out there? Starry, starry night, looking at the Milky Way, making it so far away that it's impossible to comprehend. Well, upon the thought that galaxies shine from so far, we do not see them as they are, but as they were before this earth had met. We try to understand the vastness of the universe. With measurements we sometimes curse, 'cause it's so hard for us to know how distant is the feeble light for this starry, starry night. Now here's the second one. When we found the universe. Not so long ago, astronomers tried to explain the theories that were on their brain about what a spiral nebula could be. And with modern eyes and instruments that measures well, they solve the mystery to tell. Nature of island galaxies. For Hubble came along and found that blinking star to say Andromeda was far away, much farther than the Milky Way. That Cepheid is blinking still. I guess it always will. Now the last word in astronomics physics. Starry, starry night. Contemplate the universe. Starts with a gigantic of energy and matter long ago. All that came to be from a singularity. Expansion that today we see in cosmic radiation everywhere. Dark mass and energy are cosmic stuff we cannot see, which constitutes a mystery that we continue to explore. This universe has secrets still, yes, it always will. Any questions, I'll try to answer them. Well, we really needed some more answers. What's that? I have a question for you guys. I know when I first started looking at this, when I first found that book up in Roscommon, I started looking at that. I'd heard about dark matter and dark energy, but I had no clue well what we were talking about. And I was in reading some further literature. I was trying to understand how how these concepts came to be. And I hope I've explained it in a clear enough way that you might understand a little bit of how it came about, how it came about. I mean, it had to do with the observation of anomalies in the motions of galaxies and galaxy clusters that essentially discovered dark matter when Rubin did that, and that led to the competition. And I thought that was really a comical thing. The physicists and the astronomers had a real competition for 3 or 4 years trying to figure out how much that dark matter, that increase in dark matter, was slowing down the expansion of the universe. And they both came to a conclusion, separately and independently, that it wasn't slowing down, but it was increasing in its rate, and by about the same amount. Anybody? Yes, sir.
Yeah, they finally got any more because the James Webb. What you're talking about there?
I have no clue. I'm guessing the web, that's probably on its agenda, exploring these kinds of matters.
Rather will change this picture of the universe. But at the same time, in another year or two, degree of clarity on that. But with the new instrument, then what? Your revelation. This is why we build it.
Anyhow, if you're a young person starting off your career, think about it. Be a great thing, great field to get into. Well, thank you all very much, and see you next time around.
Good summary of the history of the astronomical findings, but Hubble benefited from the people just that work.
I'm just sitting down. You've opened so many pages here, I'm not sure it'll ever shut down. I'll let you do it, okay?
All right, so we on Sky? All right, so that's the end of this meeting. Thank you very much for coming. Our next meeting will be Thursday, September 20th, and live in person at the Macomb Community College. Our next open house is September 23rd, the same night as Astronomy at the Beach. And we should be leaving here early enough to go to the Red Coat Tavern at Woodward, north of 13 Mile. So good evening, clear skies, everyone. Good night. Okay, so